Okay, so today we're happy to have Greg Gabadadze from New York University. He'll tell us about the new gravitational action for the Trace-Anomaly.
Thank you. Now probably you can tell why I was asking over lunch if there is a ChatGPT program to convert handwritten notes into PDF. Next time I'll do that. For now, if any equations are not clear, I'm happy to write them on the blackboard, or please stop me and I'll answer the questions. So this is something based on work of this year, another one with Massimo Corrati, and there is a work in progress. General theme is to look at effective Lagrangians which could capture quantum anomalies in them. So as we know, anomalies are quantum phenomena, I think the ones that we're talking about, and they arise upon quantization through loop diagram calculations. And there might be some virtue, or there is a virtue actually, to have some effective field theories in which those quantum effects are already captured, so that you can just write down the equations and then solve PDEs potentially, and those PDEs would be capturing your quantum effects. So that's the idea. Obviously, this is not always possible, but there are some cases in which this seems to be possible. And in particular, I'll be focusing on the scale anomaly, gravitational scale anomaly, which I'll remind you and define you what we're talking about. But before I do that, I would like to go through a toy example, which all of you know something about, and most of you know everything about, because that's exactly a solvable model. It's a 1+1 dimensional Maxwell theory coupled to a massless 1+1 dimensional fermion called the Schwinger model. The Lagrangian of that model is written up there. This one. And the specificity of the model is that the coupling constant, let's say electric coupling constant, has a dimensionality of mass. That's easy to figure out from what's written there. And besides the space-time symmetries, which is two-dimensional Poincare symmetry, there are two internal global symmetries. One of them is gauged, so the vector is gauged U1, but then there is an axial symmetry as well, because fermion is a massless field, and at a classical level, as it's written in that Lagrangian, those are exact symmetries. As a consequence, the vector current is conserved, and we maintain that condition upon quantization, but doing so, there is no way for us to maintain the conservation of the axial current. As you know, there is a clash between those two symmetries, and we make a choice upon renormalization, and the choice is based on a physical condition that we want the charges to be conserved while we give up the conservation of the axial current. And that's the non-conservation of the axial current related to this one loop diagram. It's a two-point diagram because we are in 1+1 dimensions. And analogous story in 3+1 is, of course, as you know, the famous triangle diagram. Now, I would like to write down some Lagrangian, which will capture this effect at the classical level, or rather through variational principle in that Lagrangian. And that's also well known. Well, thanks to Coleman, we can skip lots of details and write a bosonized version of the very same theory. In that version, the vector current can be expressed through derivative of a scalar phi, and then there's the epsilon tensor in front. And from that expression, you see that this is exactly conserved because the anti-symmetry of the epsilon tensor. And there is a magic relationship, very nice relationship in 1+1 dimension between gamma mu times gamma 5 and epsilon mu nu times gamma nu. That's the consequence of 1+1 direct Clifford algebra. And due to that relationship, you can then necessarily get this expression for the axial current. If I now use this bosonized versions of the expressions for the currents, then the Maxwell equation will rewrite as follows. The right-hand side is just the vector current here, written in terms of phi. And the axial equation, the anomaly equation, this one, will be just box phi equals to E times F dual. That's analogous F dual. divided by some constant. So these are now entirely bosonized equations. And you can ask, is there a Lagrangian expressed in terms of these fields such that variation, classical variation of the Lagrangian gives rise to these equations? And that's also well known. There is such a Lagrangian. It's this one. It's also the bosonized version of the initial theory. So you've got the Maxwell term, and then there is a kinetic fixing between the scalar and the gauge field. And then there is a derivative of scalar. And for this example, I mean, time is plus and space is minus, so that this is the right kinetic term for a scalar. And so you can easily show that the variation of this gives you these two equations. Hence, that's the goal that I wanted to achieve, have a classical Lagrangian through variation of which I get the anomalous equation. That's the anomaly equation. Okay. So we know that this theory describes just one massive degree of freedom, and it's also easy to figure out from this, but that's kind of somewhat different story. So I would like to achieve similar goal in the context of classical gravity coupled to quantized fields and capturing trace anomaly. Okay. Sound that doesn't move.
Yeah, a question.
Yes.
Sorry, the two theories is kind of the same theory or just the classic?
Well, in this case, there is exact equivalence because of the specific nature of this theory. It's exactly solvable. But in the real big theory that I'm about to discuss, it will be an approximation. And I will specify as to what approximation that is. Well, thank you very much. I'm sorry. Yes. Okay, so let's go to 4D. And unlike in the previous case, I'm going to jump to the opposite metric conventions, minus, plus, plus, plus. And this is just a reminder. If you look at, let's say, the simplest theory with a gauge field, again, Maxwell theory with a massless fermion, now in 4D, there is what's called a trace anomaly. So trace of energy momentum tensor is no longer conserved at the quantum level. Or in other words, the dilatation current, which is related to the energy momentum tensor, is not conserved. And that's proportional to the beta function of that quantum field theory times the field strength squared. Now, this relationship is the one between Heisenberg operators of the quantum field theory. But that's not what we are going to be doing in the context of gravity. So what we're going to do is to have classical dynamical gravity coupled to some quantized field, let's say massless fermions or gauge bosons or any sort of matter fields. And we're going to be looking at the expectation value of energy momentum tensor in the presence of quantum effects, quantum loops of those fields. So that's what we're going to be doing. So you can define this object very carefully in terms of the partition function. So this is a partition function in which you integrate with respect to the matter fields, but you don't integrate with respect to gravity, and gravity is still full dynamical. There is the kinetic term and so on and so forth. This is not just an external field, right? So this answer has been known for a long time as well. So in the classical theory, the right-hand side would have been zero if I took just the massless stuff, scale invariant stuff. But at the quantum level, there is a breaking of scale invariance. Because there is a clash again between two symmetries, that symmetry and diffeomorphisms, and therefore there is non-zero trace, which can be expressed in terms of the Euler density. A is some constant. It depends on number of fields and representations, but think of it as some constant. And E is the Euler density, which is written here, Riemann square minus 4 times Ricci tensor square plus which is scalar squared, and W square stands for the square of the Wild tensor, which in 4 dimensions is this. And in terms of the diagrams, this was first discovered in these papers, but then subsequently worked out in more general form. And so if you write down the trace of the Einstein's equations, the left-hand side is just Ricci scalar times Planck squared. As usual, on the right-hand side, you should have trace of energy momentum tensor, which ordinarily would have been zero in the theory. In this particular one, or whatever violations you may have for your scale invariance, the masses and such. Those are not what we are interested in, although they are always there. But this is the term that we are interested in. This comes from quantum loops of the matter fields.
What's the trace-free version of that equation?
It equals to 0. Trace-free equation, you mean when
Yeah.
classically this is just I picked a simplest case in which I only have, let's say, one massless field.
No, sorry, I mean, that's the traced Einstein
Oh,
equation.
the trace,
Yeah.
the full thing.
Yeah, what's the
Well,
version where you restore the?
I'll show you, so that will be part of the conversation, yes. So and then we need an effective action from which you can potentially derive that, or not potentially, you can derive it, which would give you this equation. Okay. Now, obviously, this question has been asked long ago, and the first two papers, which partially answered them, but in a ways actually fully answered them, were by Rigert and Fratkin and Zeitlin, and this is Efim Fratkin. That's not your neighbor from your neighboring institution. So that's Efim Fratkin. That very often this construction goes under the name of Rigert action, although those papers are actually in the same volume of physics letters P. The question would be find SA tilde I call for in this case as a functional of the metric such that trace of the variation of that with respect to the metric gives you this. And these papers argued, but I'm pretty sure there were papers before that you cannot have a local functional like this, depending only on metric, which would give rise to this property. But they made it very explicit. So because of that, what they did in particular, Rigert, is that, well, let's split G mu in terms of, conform, let me call it conformal factor for now, into 2 sigma x times some G bar. Well, obviously this is an arbitrary split because there is a conformal transformation of G bar and the shift of sigma, which compensate one another. So these are not well defined. But he said, let's fix the determinant of G bar, in which case this would be, a well-defined split. A definition for the split. And then let's calculate the effective action. So what's written here is SGR refers to action of general relativity, where instead of G, I just wrote e to the 2 sigma G bar, but this is just conventional GR written in Jordan frames, but it's the same thing. While SA of sigma G bar would be that anomalous action, variation of which would potentially recover this. Okay. Now, both of those works arrive to the same answer, to this one. So it's a little lengthy, nevertheless, it's not arbitrary. All the terms in it are very special, some certain ways. So let me go through them. This is that sigma field times the Euler density written in terms of G bar. Everything here is written in terms of G bar. This is the Einstein tensor constructed with derivatives of the sigma field. This is what's called a cubic Galilean. It's a higher dimensional term. In modern language, it's called cubic Galilean. Back then, it wasn't. And the specific nature of it is that, so you have 4 derivatives in this term, as you see. So you would worry that the equations of motion, which arise from this, would have more than 2 derivatives acting on a field, and hence the Cauchy problem won't be well defined and such. But they're not. It has very specific structure, so that the equations of motion are still second order. And this is also called quartic Galilean, although that term has been known for a long time. It also has trivially that property that you said. Equation of motion always have only up to 2 derivatives, not more than that. And they come with specific coefficients such that when you take a variation, you get what you need. It's not obvious. So for instance, if you take variation of this with respect to sigma, obviously all of these terms contribute. So this gives you something resemble what you want, except that written in terms of G bar, and this gives you very complicated expressions with derivatives. However, when you then conformally transform back to G, all of those terms combine into just E of G, Euler density of G. So that's how this works. And as to the C term, this one is conformally invariant. You can write this in terms of G bar or in terms of G, it's the same, there is equivalence. So when you vary it with respect to sigma, you're gonna get the C, so-called C anomaly. Now, I'm gonna make some comments about the literature because back then, Rigert in particular, he thought this not to be covariant for reasons that he imposed that condition on the determinant of G bar. And after that, he started to look at covariant but non-local action by re-expressing G bar and sigma in terms of G and invariance and so on and so forth. And that process leads to something complicated, non-local, and in fact introduces unnecessary additional degrees of freedom, which are ghostly degrees of freedom, because it does some field redefinition which involves forced derivative in it. And that's absolutely unnecessary. Nevertheless, that's in the paper, although this part is also in the paper. Fradkin and Zeidman, they stopped at this level and pursued their goals. Now, this whole thing was put on strong field theory footing by Komargodski and Schremer, a lot later, of course. They wrote this paper in which they proved the A theorem. That's a theorem that says that this A, as it runs with renormalization group, it decreases in the infrared. And for that, they used it. In fact, they re-derived this Lagrangian from basic principles of effective field theory. And then from that construction, it is obvious that this is the right Lagrangian. In fact, what Rigert should have said is that, well, let me remove that constraint that I had. Let me treat this G bar as a tensor field which transforms under conventional diffeomorphism as a tensor. And this is diff invariant and gives you exactly the anomaly that you want to have. It's as simple as that. So another kind of justification for that is that this very term arises as a Vesumino term in a certain coset construction. For instance, if you ask a question, can I start with some conformally invariant theory, unspecified, and then assume that conformal invariance is broken, or part of it is nonlinearly realized, and what's realized linearly is Poincare. So this is a conformal group in 4D, and I want to coset over the Poincare group in 4D, right? So the dilatations and the special conformal transformations are spontaneously broken, while translations and Lorentz boosts are preserved. So that's a coset, and then you just follow regular methodology of construction of effective field theories, which have been developed, Vesumino, Hallan, and many others following with space-time symmetries, with Ogievetsky, I think, and then Volkov and others. I don't have everybody on my fingertips, but those groups, and you will see that you will recover some effective field theory terms in your Lagrangian, and then you will also find one Vesumino term, which you can represent this as a five-dimensional term projected on the boundary, and that was found in this paper. It exactly coincides with this Lagrangian as well. So you just get that construction. There is also a way to get that from actually one-loop calculation. So the point is that this is on a solid footing at this point. So this is the answer for the question as to what's the effective renormalized in this way Lagrangian, which gives you which captures the anomaly, the scale anomaly. That's the one.
The 5D term is local or non-local?
Which one?
You said there's a 5D Vesumino term for this?
5D term is local, so it's a total derivative. Once you take it on the boundary, so this is what you'll get.
But if local is a function of, say, G.
It's a local of 5-dimensional G. Yes. So to that point, that's a good point. Let's say if you were to do one-loop calculation, another, that goes in the same direction. let's say you do dimensional regularization. You can write that counter term as a local 4 minus epsilon dimensional term. Once you, but there is an infinite coefficient in front. If you vary that, so you're gonna get infinite coefficient times coefficient that goes 0 when epsilon goes to 0, and that gives the finite term. That's in the Lagrangian. But there is also a way to do exactly the same in the context of action. So when it's d-dimensional, not 4-dimensional, it's all local. In order to reduce it to 4 dimensions, either you have to go to non-local expressions, or you have to have additional field, which is this sigma. So in some ways, you can compare this also with 2-dimensional Polyakov Lagrangian, right? So that Lagrangian is R1 over box R, and it's very easy to integrate in one field, let's say phi, which will have kinetic term plus phi times R. Here it's a lot more complicated.
G, capital G
Oh,
bar alpha beta, what is that?
The Einstein tensor in terms of G bar.
The West-Domino term is A or C?
The West-Domino term is the A term. This will come up as the West-Domino term in that construction. The C term will come up as regular, yeah, as a regular, effective term, yes. Okay, so now what's the problem? So why this is not an answer? Well, by the way, I mean, from this you can derive full G-mu variation. You're gonna get something very complicated, but well, we have the expression for so. But so what's the problem now? The problem is this. So if I rewrite now this Lagrangian in terms of the original metric G, so in the Einstein frame, right? So the GR part would only depend on G, because that's the definition of GR part. This part, I denoted it with SA prime, but it will still depend on two fields, on sigma and G. And in fact, it will have exactly the same structure. Think of this, all sigmas replaced, well, sigmas kept as sigmas, bars replaced by unbarred quantities. And then this sign will go into plus and this sign will go into plus. Other than that, it's the same. So they're just exact, transformation of that term. The point is that in this language, you still have this term, and of course this term as well. And the reason that why that's problematic is because now your sigma term, sigma field, has no kinetic term whatsoever, right? It got absorbed into here. While your nonlinear interaction terms, they do have derivatives of sigma. Well, obviously that's a stick theory. You can describe the thickness in many different levels. Well, classically, Hamiltonian dynamics is very hard to construct, but not only very hard, the Cauchy problem is not well defined, but more in terms of quantum fields, you can do following exercise. This is well-known exercise, obviously. If you have, let's say you have some higher dimensional operator and kinetic term with some coefficient C, and let's say this coefficient C goes to 0, well, you can rescale this so that it converts into kinetic term, but then higher dimensional operator down by this Z, and Z going to 0, meaning that this goes into infinitely strongly coupled theory. So the scale at which that becomes strongly coupled is 0. And hence, on Minkowski space, this is a infinitely strongly coupled theory. So that's a problem. Of course, you can do various things, such as say that, oh, I always define on some kind of background. This G mu will have some value, and then if G mu has some value, that gives a kinetic term. But that kinetic term will be sign indefinite. It will depend on your background. For instance, for ADS will be one sign, for the DS will be the other sign. One of them will be a ghost. Or that'll have to be even Lorentz invariance. You can have all sorts of issues with propagation, superluminal, and so on and so forth. So that's not a productive way of proceeding. You want this theory to be defined on Minkowski space in a proper way. So you want some sort of kinetic term for that sigma on Minkowski space. So to understand what we can do about that, let me dig a little bit deeper to trace where this is coming from, the lack of kinetic term for that sigma, and that's related to the fact that in general relativity, the conformal mode is not a dynamic propagating degree of freedom. Right? Let me be very careful about that. As we know, general relativity has two physical propagating degrees of freedom. Those are helicity plus and minus, plus 2 minus 2 states of massless graviton. Everything else is not dynamical propagating degrees of freedom. And in regards to that conformal mode, this is how it emerges. Let me do a simple exercise, expand this around Minkowski space, and that's relevant, of course, for background as long as your energies are higher than curvature. And standard expansion this is my lapse now, and this is my shift written in terms of transverse vector and the longitudinal part of the vector, and then Hij I decompose into transverse traceless tensor. This is transverse vector, another one, and this is the longitudinal part of it, and that's the conformal mode. How, right? So rho and u are gauge removable. Let's say we remove them. You got to check that there's no constraints, lost when you do that, but they're not. They're not. And then the tensor part and the vector part and the scalar part, they separate. They don't talk to each other anymore. And for the scalar part, this is what you get. You get minus 3 times tau dot squared plus derivative of tau squared, which already looks kind of bad because this sign is a ghost sign. This is just time derivative squared. That's a ghost. And also it's not Lorentz invariant, as you can see between the two. But luckily, and this is GR on flat space. But luckily there is a constraint. Because if there weren't constraint, this would be a very problematic theory. So there is a constraint. Variation with respect to n tells us that the Laplacian of tau has to be 0, and then with proper boundary conditions, we can have tau only time dependent, okay, but not a propagating degree of freedom. So by the way, this is the basics of FRW cosmology. This tau is nothing but the scale factor or perturbed version of it. And when we write the Friedmann equation, which is a dot squared divided by a square equals to, let's say, kinetic term of a scalar field, right? So let's say we have this. Some coefficient here. Right? So if A was not a ghost, obviously it would have a different sign, and you would never get proper Friedmann equation. The reason why it's proper and gives you what we want is precisely because it has bad sign there, and then it's equals to the proper sign, right sign for the kinetic term for an arbitrary scalar. But at the same time, it's not propagating. It's just constrained. Okay, so that's what we need to somehow relax, but relax in a way that there are no bad degrees of freedom, that all degrees of freedom are still nice. So here is a proposal. Let's just try, and then we can argue as to where it might be coming from. So before we add the anomalous term, we can modify or extend the GR term with this. So this is the GR term written in the Einstein frame, and this is the kind of also GR term, but written in terms of G bar now. So it's diff invariant because both G bar and G are tensors. And there is no two tensors, obviously. There is only one tensor and one scalar field in this theory. You can choose which one you want to work with. But it's kind of convenient to write this way. Reason why it tells you as to what's going on. So here, this piece will give you the kinetic term for that conformal mode, but it has to have wrong sign as compared to the GR term in order for that kinetic term to have the right sign. precisely because of what I just described. So if you just take GR and stick in the conformal mode, you're gonna get the wrong sign, right? And for that to be right, you have to have minus. So that's the theory, and then you can do the same, exactly the same exercise. And in exactly the same exercise, you will get the old Lagrangian, but you get an addition, that addition proportional to m bar squared over m squared. This is what it is. And now your constraint gets modified, and that constraint relates this tau, the conformal mode, to this sigma, the degree of freedom that you introduced. And if you plug back, you get the right sign, kinetic term for either tau or sigma. You can think in either language, whichever you prefer. But there is only one mode, the conformal mode. It became the dynamical now in this theory. So I'm going to call this theory R minus R bar. But again, this is just a scalar tensor theory. There is very kind of special type scalar tensor theory. Okay, so
Can there be field configurations which overcome that small ratio? Like can R bar be very large when R is very small?
that's a conditioning on m bar and also phi.
But M bar and M are just some constants, right? So
Yeah,
the question is just, can there be any field configurations that overcome
yeah.
any ratio you pick?
Right. So that's a condition on the scalar field. I'm gonna rewrite this in a second in more. Okay, so let me maybe here, yes. So what you are asking is that this is that R bar term.
Yeah.
Right, so what you are asking is if phi can overpower m, phi has coefficient m bar, which is less than m, but then there's still the dynamical question.
Yeah.
And the point is that you shouldn't be going beyond the effective field theory, which is in that realm, you can explicitly show that in fact this is always the case, assuming that m bar is smaller than m.
I see. So we're in an effective field theory where we have a derivative expansion and a constraint on the range of the fields that field.
That's exactly right.
Yeah.
Yes. So and so that's a condition that I'll be using m bar. I don't know what that scale is yet. So when I will have construction from which this comes out, you will see what that m bar scale is. But numerically, even in that construction, we don't know. It's kind of experimental question if this theory has something to do with the nature, and we will see what the constraints might be. But before that, I just want to point out that there are some symmetries. This is a symmetry which exchanges actually these two pieces. So this is an exact symmetry of this Lagrangian. It's also easy to understand how it is a symmetry. And then there is a duality transformation, m exchange in m bar, g to minus g bar, and sigma to minus sigma. That has exactly something to do with the fact that I pointed out that that anomalous term actually, that anomalous term under the duality exchange goes into the anomalous term written in terms of sigma and g. Precisely that transformation. Okay, so this slide is a little bit out of order. I'll talk about this a little bit later. I wanted to move to the next one.
Wait,
Yes.
Please understand, Gregory, there's a bound on how big phi can become, or? I mean, you want G hat to be positive, or you don't care?
I want G hat, you mean?
Yeah.
Yeah, so G hat is another object I didn't talk about, but you can define this object, which is also invariant under these transformations. And it will be related to G this way. Well, obviously, I want my phi to be sub-Planckian always, right? So that's a condition. And the reason why I want sub-Planckian, and actually I should have said that, this theory is amended by infinite number of operators which are suppressed by the Planck scale. I want the operators that I'm discussing to be well separated from all those scales. In fact, these anomalous operators will be well separated from them. Well, already in this sixth theory they are, because their suppression scale is 0, right? But we want to make it finite, but a lot smaller than m Planck. And that will be the strongest conditions on my fields. But before I've gone to higher dimensional operators already at this level, because we know GR has 1 over m Planck corrections, you know that this should be satisfied, that this is always smaller than m. Okay, so here is the full theory now. Let's put things together. This is the GR term, but rewritten in the Jordan frame. And this is the new term, the R bar term. And here is the A anomaly term, and here is the C anomaly term. And shorthand notations I'm using now is this G is the Einstein tensor. This G3 is the cubic Galileon, and this G4 is the quartic Galileon. Okay, so they all depend. This all depend on sigma. And then this part, the property that I was alluding to, that you only get second order differential equations, that goes back to Hondensky, who wrote down the most general expression for a scalar tensor theory of gravity, which has two derivative equations of motion obviously without thinking of anomalies or anything else. That was his general classification he did. So this is part of that huge class of theories, actually, Hondensky. And there was another paper by Pedro Fernandez, who also imposing very interesting classical constraints without any reference to anomaly, discussed this kind of theories. This term, though, is not in the Hondensky class. For instance, this one, the C anomaly, would have given you higher derivative terms if you were to vary that with respect to the metric. So Clay, going back to your question, you can from here, obviously you can derive the full equation, and it's there. It's somewhat complicated, but it's consistent with everything else. You got 11 equations now, and for 11 fields, 10 in the metric, and 1 in your sigma field. So all of them are second order equations. Now, how about this strongly coupled behavior? What did we achieve? Where does this theory become strongly coupled? You can do that. Some details are on the slide that I skipped, but I don't want to go necessarily to that. It's formalities in terms of separating scales and discussing what happens in the decoupling limit. If you ask me a question, I'm happy to do that. But the simplest exercise you can do is to ask at what scale this sigma field now becomes strong. And you can do it various ways, either doing this decoupling limit, which is described on the slide, or you can just do through this substitution, which is equivalent. So you will find out that you have scale invariant or conformal invariant kinetic term for that scalar. Now this pi is rescaled, properly rescaled sigma. And then you have this cubic Galilean term and the quartic Galilean term, both of them suppressed by this M bar. So your new strong scale for that sector, for the scalar sector, is M bar. So you can trust your theory until that scale. And M bar is a lot less than M Planck. So all those string theory operators, which are suppressed by M Planck or close by string scale, are subdominant as compared to this, as long as M bar is a lot lower than M Planck. And that's the regime we're thinking. So you can be thinking of this M bar as a scale of scale invariance breaking in some sector of your theory. And the sigma is an Ambu-Goldstone boson of that symmetry breaking, except that its symmetry is also anomalous. So you get both. So this term would be nonlinearly realizing that scale symmetry, while this term is just anomalous breaking of that symmetry. And so, okay. And this one, as you know, GR, of course, explicitly breaks that symmetry. So you now have all three terms. You have explicitly terms of explicit symmetry breaking, terms of spontaneous symmetry breaking, terms of anomalous symmetry breaking. All that very same symmetry. Okay, so some consequences. Actually, Shinji Tsujikawa, he solved for black holes in this theory. Not exactly, but he solved, he got solution as an iteration in this term, and found out that there is fifth force. Of course, you would expect that because there is an extra scalar. Fifth force, which is suppressed by M bar over M Planck square. So this would put some phenomenological bounds on M bar, of course. This has to be, 10 to the minus 10 or something, at least. And so those black holes have no hair.
So question?
Yep.
So this Galilean is supposed to model or be an EFT for the kind of matter sector that had a trace anomaly and is coupled to gravity.
It's coming from two factors. One, what you just said, but there has to be the scale of the spontaneous scale symmetry breaking,
Mhm.
which gives you these terms.
Yeah.
Right? If I go to the previous slide, they're more better visible there, right? So these two terms are just scaling variant version of GR, as you know, right? So there has to be a sector which has that scale, symmetry breaking, which is this, and that's a scale.
So you're describing a kind of phase of gravity plus matter where there is this symmetry breaking.
That's
It may-
exactly right, yes.
And
Well, it has to be, otherwise this is a meaningless theory.
Mhm.
That's a point that, well, let's do.
and is there an example where you can actually match to a microscopic?
Yeah, I'm
Okay.
about to discuss that, yes.
So what sets the zero mode of sigma? There's a constant value for sigma, presumably.
No, sigma is a dynamical field.
Right, so it in principle has a zero mode, it has some asymptotic value. You just taking that
It's
to
like
be,
the scale of the conformal symmetry breaking. It's like, the moduli space VAB or something like that.
You mean the phi?
but it's
Yeah,
it's free.
Phi, okay, so you're asking about, so phi is a basic field. Yes, this is exactly the modulus that parameterizes your scale symmetry breaking. And fluctuation about that, which is sigma, is an Amundsen boson of that symmetry breaking. And as you see, phi has the potential, so this thing is arbitrary. That's a modulus, right?
Okay, so you just pick it.
Yeah. Yeah, you don't know what that is.
So should I treat that effective action then as classical at the end?
No,
The MM
no,
bubble?
because it has quantum effects in it. So that anomaly term came from the quantum loops of, this term comes from the quantum loops. And this one too, these two come from quantum loops.
Right, but this action itself, do you want to treat it now as a quantum action or as a classical action?
This is a quantum effective action. It includes quantum effects already, but when I do classical variation, I get equations which already capture those quantum effects.
I mean, I would have expected sigma to be lifted by loops in this theory.
Well, in this theory, but here I've already taken into account quantum effects. Non-perturbatively, it might be, to which I will come, but perturbative loops are all in there.
Okay, so you say it's an exact modulus
Yeah,
in theory.
in the theory is an exact modulus, yeah. Modulo non-perturbative, I will mention something about that. Okay, now the microscopic, where this could come from, this is what we did with Massimo. Turns out, at least in some limit, you can really deduce this from a theory which is not strongly coupled at M bar. You can go above M bar and all the way to higher energy scale of that theory. And well, it's very surprising that it turns out to be one of the ADS, five-dimensional ADS geometries, which is capable of reproducing all of those things, in particular in the context of Randall-Sundrum model. And let's proceed step by step. I'm going to take now large NC limit, because only in that limit we have this duality. And in the large NC limit of CFT, A and C coefficients are the same. And then that anomalous term combines into something, well, relatively simple as compared to what it was. It's this combination of Riemann tensor Ricci scalar with NC square in front. And this was done, Henningson and Skanderis, who showed that actually in the ADS construction, you do get this trace equation from five-dimensional ADS. But they have not written the action, obviously effective four-dimensional action, which gives rise to this. But you can do that. And here is a way to do that. If you take now, let me take Randall-Sundrum with one brane first. So this is called RS2, usually, just one brane. So this ADS5, and this brane provides kind of UV cutoff for your dual CFT. You can integrate out the bulk order by order in this parameter, R in L square, and I left out a references which I should have written. There are two papers by Kant and Soda in the beginning of 2000s, and there are wonderful papers actually who did this integration out, and they are referenced extensively in our paper. I'm sorry I left it out here. So these are their results actually. Well, calculation is their result, and so you can expand, and then you can look at the junction condition on this brane. It's a regular Israel junction condition on the brane, which in this case is this, and then substitute expressions for the extrinsic curvature. Now, point is that general expressions for the extrinsic curvature, they're non-local, because you integrated the bulk which has continuum of modes without any mass gap. But the interesting observation is that the traces of those extrinsic curvatures, they are local. And you can use that fact combined with this trace of the junction condition, in which you substitute this, you use the standard Randall-Sundrum fine-tuning, and then you derive this equation remarkably with the right coefficient. This coefficient, as you know, according to the ADS CFT dictionary, is just a central charge of CFT, which goes as NC squared. And the right structure for large NC limit. Okay. So now this is not new, this just recovers their results, but combined with, but placed in a theory in which you do have graviton zero mode, that's a Randall-Sundrum zero mode. That's an additional incremental step here as compared to Henningson and Skenderis. And the next step you can do, once you have this equation, you can lift it into some effective action, and that's very easy that we know how to do after Riget. So you will just lift the inner action, and you're gonna get that action that I just described. The anomalous action. This one. So you'll get this exactly. So ADS5 has in it that action effectively. Now, I didn't show you yet the kinetic term below, and the reason I didn't is because I didn't have another brane. So that kinetic term now, it will be related to the existence of the other brane, and as you know, from the ADS CFT, that is a kind of spontaneous breaking of scale invariance that has been known in the ADS CFT context for quite some time. And if you do that, this is what you get. Here is your 5-dimensional metric. Here is your zero mode. This is fluctuations about zero mode. You integrate them out. You do this expansion. You solve some of the bulk equations, and for the zero mode, then you get this effective action, in which omega is the kind of Ward factor, but it's a general Ward factor. It depends both on z and x. Then, as you see, you can exactly integrate with respect to z from 0 to some ZIR, where the second brane is. But the difference from conventional cases is that you allow for that second brane to fluctuate, of course, and the fluctuation of that is denoted by this field chi, which is related to that precisely the sigma. So if you plug all that in, then it becomes clear as to how do you get the minus sign in front of the other curvature term. It's just the integration in the z direction, because you integrate from A to B, so it's value in A minus value in B. So that's how you get the minus sign. But the difference in the coefficients are a difference in the behavior of this Ward factor. Now it also explains how you get the hierarchy between Mn and bar. Well, it doesn't explain, it just gives you a different notion of that hierarchy. So if ZIR is a lot bigger than the radius curvature of ADS, then this is precisely the hierarchy between M bar and M that you need. And ZIR bigger, a lot bigger means that, right? So your kind of interval is much bigger than ADS curvature. You are mostly in RS2 as opposed to RS1. That also means that your Kaluza lines, because of that compactification, are lighter than the inverse radius curvature. And therefore, it's not surprising that collective contribution of those Kaluza lines gives you those very complicated nonlinear terms. That's where they are coming from. You cannot just ignore those Kaluza lines. Oh, well, moreover, in the language of ADSC dictionary, you know what M Planck is. M Planck is MC divided by L. And this M bar turns out to be NC divided by ZIR. And just because L is a lot smaller than ZIR, so that's the hierarchy between an M and bar. And this is what I just said. Kaluza-Klein masses are a lot smaller than the M bar because there is NC difference between them. So you're gonna get still infinite number of Kaluza-Klein, even though now you have discrete spectrum of Kaluza-Kleins because you compactify.
Where is the field sigma?
Yeah, sigma came through this. Sigma is essentially, if I fix the coordinates so that this is straight, this should be able to wiggle, and that wiggling is capital phi, which I called before, exponent of which is sigma. And this location is that modulus actually that we're talking about. This is that modulus position of the frame. Now, so you can ask if there is departure from this large NC limit, because this was all NC squared, leading NC squared terms. Apparently, it turns out there is. We worked out that in the paper, but I don't have that in detail for the sake of time. So the way you can do this is you can put additional QFT on this brane. This is a positive tension brane. You can put localized QFT on it. So that QFT will have loops. Through those loops, you generate additional A term or correction to the A term. So the A term will get shifted as compared to the C term, of course, in general QFT. And that will give rise to 1 ONC corrections to this result. So even that part you can recover. Other way of recovering that part is to add into the bulk the Weyl tensor square, 5-dimensional Weyl tensor square, or 5-dimensional Euler density. But once you do that, you are introducing another scale by hand. So that has that disadvantage. While in this language, you don't need to introduce any scale. So one last comment and before conclusions. First of all, so the question that Sal was asking, this E couples to, I'm sorry, the sigma couples to Euler density here. And you may think maybe some non-perturbative wormholes or something like that can generate some potentials for it. So with Leah, we want to look into that and see that that's possible, although we have not done calculation. But even if that happens, that will be very, very small mass, obviously, because those effects in the approximation in which those are valid, those effects are small, exponentially suppressed. But other than that, there is a fifth force, and that fifth force will be long range, even if that sigma has a small mass. And it's kind of small as long as M bar is small compared to M Planck. And there's possible cosmological consequences that we are looking at and trying to work out. But that's not done yet. So let me just summarize. What I talked about is incorporating a trace anomaly into the quantum effective action. And that leads us to the need of introducing additional terms which give rise to the kinetic term for that sigma and making that theory meaningful, effective field theory. It's still strongly coupled, that's strongly coupled at some high scale. I mean, think of this M bar as, I don't know, between 10 to the 10 GeV or 10 to the 15 GeV, something like that. That's still a high scale. But then there is a light degree of freedom necessarily. That Nambu-Goldstone boson, sigma, which may have or does have consequences for physics. And we need to work them out. So that's the stage we're at this point. So thank you.
So in the decoupling limit, does that effective action make sense for all values of A and C, maybe subject to some sign constraints, or can you derive some constraints on A and C by demanding some physical well-behavedness?
Yes, that's a potentiality that if, so the, yes. So the question would be, let's say, we go back to this area of theory, obviously, and we work out some cosmology. And on those cosmological backgrounds, for instance, once I have non-zero curvatures, so this term, instead of being nonlinear, will give you a quadratic term,
Exactly, yeah.
which will be mixing between sigma and some fluctuation of the metric. And that will modify the dispersion relation
Yeah,
for
yeah.
gravitational versus sigma. So we are looking into that precisely. That's quite possible that it can give you some constraints, but I would rather say that it will give you constraints of m bar, because all these terms are suppressed by m bar, right? So why should this get, so think of this sigma having from here, kinetic term with m bar, like I was just saying, and then all of these terms are suppressed by m bar. This one is suppressed by m bar, but also by 2 powers of m Planck. But still lower than m Planck.
But we know, for instance, that there are some linear constraints on A and C from like the Hoffman-Maldacena inequalities.
That's right.
So you might
Yeah.
ask if they could be reproduced from
Yes.
from this action.
Yeah, so that will be, if indirectly or through other considerations, you restrict m bar, then exactly what you're saying is correct. You can then
Uh-huh.
try to impose those bounds, indeed. That's all.
What is the field theory that correspond to Randall-Sundrum picture? Is that this conformal field theory that somehow remain conformal for a long time and then suddenly becomes confining? What is the what should I think about this field theory?
Oh,
Yeah.
it's just, yeah, it's just field theory with some spontaneous scale symmetry break. Well, there is UV cutoff, right? So this brain,
You be cut off by gravity, right? Because it's this
well,
M, the first.
there is a, so if I start here, define that I have this brain translates into CFT as a UV cutoff of my CFT in the dual picture. Okay,
What happened?
yes,
Yeah, yeah.
and then the moment I have this, that means that there is a spontaneous symmetry breaking at a new scale, which is this M bar in that CFT. So I've got CFT in which there is scale symmetry breaking at M bar and a UV cutoff at that scale.
You by spontaneous symmetry breaking, do you mean confinement or something?
No, spontaneous scale symmetry breaking.
Field symmetry breaking.
Yes,
But isn't it spontaneous?
it's spontaneous. Because that's an important point which was shown in the context of RS by Ratazzi and Zaffaroni, I think. So it's not obvious what the second brain does, but they check the word identities, and through that you can prove that it's actually spontaneous symmetry breaking. So there is a nonlinearly realized symmetry.
But is there a field theory example of such a?
Highly supersymmetric ones only. Highly supersymmetric. In all the other ones, typically you would lift that direction by some loop corrections or something. Yes. Yes.
In the beginning, you said how you could view this A anomaly term as coming from a West-Zumino term for some quotient
Yeah.
place. How do you understand? Can you understand monotonicity in this picture? I mean, usually
Can I-
monotonicity under RG flows. Usually we think of coefficient. Usually coefficients of West-Zumino terms are invariant under RG flows.
But only because they're discrete. If it's a non-compact
Yeah.
quotient, then it won't be discrete, so.
Yeah.
So that's
Yeah, there's no contradiction with
but it does it help understand in
No,
a different way why it goes on in one direction?
no, not that picture. I mean, you just get generic West-Zumino term and the coefficient is not
It's
fixed by
anything.
that constraint, yes.
Okay.
Yeah. In that picture, it's not even related to the number of degrees of freedom. You are doing just general coset construction.
No other questions? Yes, Gregory.
So if you do that with the axial symmetry, you get back the